Section 22.5, Lenz's law. Lenz's law, it turns out, is very closely related to Faraday's law of electromagnetic induction. It has to do with the direction of the induced EMF and the induced current. So here's the formal statement of Lenz's law. It says that the induced EMF resulting from a changing magnetic flux has a polarity that leads to an induced current whose direction is such that the induced magnetic field opposes the original flux change. I encourage you to chew on that for a while because there's a lot of good ideas packed into that definition that cover all of the process you'll be going through in using Lenz's law to solve problems. But the boiled down statement of Lenz's law is that a change in magnetic flux must be opposed by the induced magnetic field. So when you have a change in magnetic flux, it will induce a magnetic field, but that induced magnetic field is going to oppose whatever change happens. There's a reasoning strategy that can help us out here. This comes from the textbook, and I appreciate the steps to follow. So the first step is you need to determine whether the magnetic flux that penetrates the coil is increasing or decreasing. Once you've figured that out, we know that we would need to oppose the change in magnetic flux. So if it's increasing, we'll need to act against that. If it's decreasing, we'll need to support it. So find out the direction of the induced magnetic field must be so it can oppose the change in flux by adding or subtracting from the original field. When the magnetic flux is increasing, usually that means that the induced magnetic field will then subtract from the original field to oppose that increase. If the magnetic flux is decreasing, then usually we will add the induced magnetic field in the same direction to oppose the decrease. Once we have the direction of the induced magnetic field in step 2, then we can go on to step 3. It says use right-hand rule number 2 to determine the direction of the induced current. Remember, right-hand rule number 2 was the one where we said that our thumb is the direction of the current, and then there's an induced magnetic field around any current. So the induced magnetic field comes from the fact that there's an induced current. Now that we have a sense of the steps in the reasoning strategy, let's try it out with an example. Conceptual example 8, the EMF produced by a moving magnet. A permanent magnet is approaching a loop of wire. The external circuit consists of a resistance. Find the direction of the induced current and the polarity of the induced EMF. All right. So as we look at this, our first step in the reasoning strategy is to figure out if the magnetic flux is increasing or decreasing. So in the scenario, we know the magnetic flux is changing because this magnet is approaching the loop of wire. As it's approaching the loop of wire, the magnetic field is going to be increasing. So the overall flux is also going to be increasing as time passes. And the magnetic field lines are shown here in red. And so it's going to effectively be more and more magnetic field lines passing through this loop. That means for step 2, we're going to need an induced magnetic field that opposes this change. So we'll grab green for that. So our B induced opposes the fact that our flux is increasing. So our magnetic flux is increasing because the magnetic field, because there's even more of it pouring through to the left side. So what's the direction of our induced magnetic field to oppose that change? We're going to need to induce a magnetic field that acts opposite the increase. So that at the center of the coil, the induced magnetic field is going against that change. Once we know that, then we can think about our right-hand rule and lining our fingers are going to be the magnetic field going through the coil, and then our thumb can give us the direction of the coil, right? So you can try some different orientations, but if I'm wrapping around a coil with my thumb, the only way I can get the induced magnetic field to point to the left is if I follow this counterclockwise current. And I encourage you to try this out with your own thumb and fingers, right? That as the current goes up and over, the induced magnetic field in the center of the coil will always be pointing to the left against the oncoming magnet with the increasing magnetic field. Now this idea, or this illustration, is highlighted with two different instances which can help you if you're struggling to get your hand oriented properly. So let me clear some of that to make more space. There's two different ways that the current can be induced. One is this clockwise direction, and the other is this counterclockwise direction. If it's in the clockwise direction, then your thumb is coming over and at you. That's the easiest way I have to do it, so try that out with your thumb. And the magnetic field lines wrap around, as is shown with the fingers here, and point to the right. That would be the induced magnetic field. The one on the left is the one closer to what we just talked about, right? Where the induced magnetic field lines point to the left because the current is going counterclockwise. So the one that will actually match our picture here is the second one. And that's where Lenz's law is really valuable, because we can figure out the direction of the current. And if the current is flowing that way, then to the resistor, what it looks like, if the current is able to go from A or through the resistor to B, then it looks like point A is the positive EMF side of the EMF source, right? Versus B is the negative side. That's the polarity of the induced EMF, if you will. But the induced current does just fine to convey that. Now, I know the right-hand rule is tricky, and we've seen a lot of different ones, right-hand rule 1 and right-hand rule 2. So I found a resource that helps with right-hand rule number 2 in particular. So first, let's take a look at our reasoning strategy to refresh our memory. Boiled down, the reasoning strategy is 1, is the magnetic flux increasing or decreasing? 2, we need to set the induced magnetic field to oppose this change in flux. And 3, we can use right-hand rule number 2 to get the induced current's direction. Now, right-hand rule number 2 is depicted here with these drawings. And if you have a straight wire, it's easiest to do right-hand rule number 2 as our book teaches it, with keeping your thumb in the direction of the current and the magnetic field wraps around or curls around. This approach also does work with a loop of wires we saw in the last example. You can get your thumb curling around it, but there is a slightly easier way. And that's a variation on right-hand rule number 2, which if you don't want any variations, you can ignore this part of the video. But if you're interested, you can flip which of your fingers is the magnetic field versus the current. You can make your thumb the magnetic field through the loop of wire and your fingers the current. The benefit of this is then your fingers are already curling around, which is what loops of wire are already doing, so it's matching that more closely. Your thumb then gives the direction of the magnetic field at the center of the loop. So you can read more about these with the links in the slides if you're interested. I'm happy to talk more about them too, because I know that it is tricky to settle in on it, and it's something that just comes with practice. So the more you can practice it, the more comfortable you'll be. Speaking of practice, let's try another example. The EMF produced by a moving copper ring. There's a constant magnetic field directed into the page in the shaded region. The field is 0 outside the shaded region. The copper ring slides through the region. For each of the 5 positions, determine whether an induced current exists, and, if so, find its direction. All right, so if we want there to be an induced current, we know there needs to be a change in the magnetic flux, where a change in the magnetic flux means that we have some sort of change in either the magnetic field strength, B, a change in the area, or in a change of the angle between the magnetic field and the area. Now the key here for this example, since the magnetic field is a uniform strength, but at times the ring is passing into the region of magnetic field or out of it, that's going to be an effective change in flux, which you could think of as a change in area in which it's acting. So the regions that don't change in flux aren't going to have an induced current. That's the easiest ones that we can start with, right? Notice position 1, there's no magnetic field, and that doesn't change. So there's not going to be any flux. That's the same with position 5. Cool. What about position 3? Notice position 3 is passing through a uniform magnetic field, constant area, constant angle between the magnetic field and the normal to the surface. So the change in flux is 0. And thus, there's also no current that is induced. Wow, so we went from having 5 positions down to just 2 that could have an induced current. Let's focus in on those 2 positions. At position 2, the copper ring goes from no magnetic field to entering a magnetic field. So how does the flux change? Well, notice you can either describe it as the magnetic field increases or the area increases. Either way, the flux is definitely increasing. We want to set our induced magnetic field to oppose the change in flux. So that means our induced magnetic field is going to need to act in the way that opposes this increase. So if we're getting more and more magnetic field going into the screen, piercing the loop, we're going to need to induce a magnetic field that is going in the opposite direction, right? Opposing this change. So it's going to need to go out since the magnetic field is going in. Now that we figured out the direction of the induced magnetic field, we can use right-hand rule number 2 to determine the direction of the induced current. So if our induced magnetic field is coming out of the screen, and here I'm going to use the second one for a loop, just to try it out. So induced magnetic field is coming out of the screen as a thumb, then my fingers curling around will give the direction of the current. So I get here that the current is going to be counterclockwise. Again, we can use the original right-hand rule number 2 just as easily and set our thumb in the direction of the current, and then our fingers are curling through the loop coming out at us. And I encourage you to try that out. All right, in contrast, position 4 is leaving the magnetic field area. So it has a decrease in the effective magnetic flux, right? Because it's losing area that's in the magnetic field. What does this mean? Well, this means that our magnetic flux is now decreasing. If our magnetic flux is going down, the induced magnetic field again wants to oppose that change, but now it's not opposing the magnetic flux, it's opposing the change in flux, so it's actually supporting the magnetic flux. It's saying, wait, we're losing, we liked having all that magnetic flux that was going into it. We got used to that, we don't want more change. So that means the induced magnetic field is going to try to recreate what it just lost. So the induced magnetic field is now going to go into the screen or page. Pretty wild, right? So the induced magnetic field is always opposing the change, whatever that change may be. Once we know the direction of the induced magnetic field, we can use our right-hand rule number 2, stick our thumb in the direction of the induced magnetic field, and use our fingers curling around for the direction of the induced current, which is now going clockwise. But that current will vanish as soon as the changes stop, as soon as it returns to just passing through an area of no magnetic field. So this introduces Lenz's law and how we can look at how the induced current is always going to be set to oppose the change in magnetic flux.